My goal in this video is to introduce you to the idea of vector. But to start, let's just talk about things we might want to measure. Some things we might want to measure in this course and outside of this course can be completely described only by a magnitude, some idea of how much. Right, and if I just think of simple examples of things like mass, length, area, and time, if I give you a number and a correct unit, you'll know exactly what I'm talking about in terms of these quantities. Right, for mass, if I say 3 kilograms, you know exactly how much, you know exactly what I'm talking about when I measure a mass of 3 grams. If I say a length of 100 yards, you know exactly what I'm trying to measure just with that magnitude, right? A correct number and a unit of measure. For area, I could say 10 square feet, and you can imagine 10 square feet. Or I could say 1 minute for time, and you know exactly the amount of time I was talking about. In fact, when I said 1 minute, nicely enough, about 1 minute of this video had elapsed. These things, we only need that one bit of information, right? A number and a correct unit of measure. These are quantities that we'll come to know as scalar quantities. When we only need that one bit of information, a magnitude, so a number and a correct unit, we call those scalar quantities. We'll understand why we call them scalar quantities, use that word scalar in another video. But for right now, we'll just call them scalar quantities. All right, other things we might want to measure require more information. So imagine I have a box. And that box is just sitting on even ground, right? Level ground, nothing special about it. If I told you I applied 5 pounds of force to that box, you wouldn't know what I did, right? You'd have questions. You'd say, well, did you push or pull the box with a force of 5 pounds, maybe in that direction? Or maybe I applied that force of 5 pounds straight up, attempting to lift the box. Or maybe I applied the force in with some kind of angle, right? Maybe I put 5 pounds of force in that direction or this direction. So right away we understand the more information we might need to understand something like a force. We don't only need a magnitude, so when I say 5 pounds, that's a magnitude, that's a how much, but I also need to tell you in what direction I applied the force, right? If I simplify my picture here and say, well, I tried to pick the box up and applied that 5 pound force straight up, due north, you know exactly what I meant. For these quantities, we'll need to measure them with vectors. A vector is a quantity that requires a magnitude and a direction. Other examples of vector quantities: velocities, acceleration. These are vector quantities. When I say velocity, right, I have to tell you a direction when I talk about velocity. If something's just moving on a number line, a plus or a minus would tell me left or right, and that was a direction. But if I have something moving in the plane or in space, right, a plus or minus wouldn't make sense. I'll need to literally tell you a direction I'm traveling in to describe velocity. If I only tell you 30 miles an hour, right, if I only tell you the number, that actually becomes a scalar quantity, and we call that speed. And we'll talk about that more later on in the class. All right, so when I want to talk about vector, I need to tell you both a magnitude and a direction. And what we use to represent vectors are arrows, exactly what I've drawn here. So vectors are represented with directed line segments, and that's just a fancy way of saying arrow. So arrows. So vectors really just arrows. The direction of the vector is literally the direction it's pointing in. Be it a vector in the plane pointing from one point to another, or a vector in space, right? I can imagine a vector that points from here and up at an angle, right? Just like the markers pointing up and away from the board. The magnitude of a vector is its length. So if I draw this vector here, that was supposed to be a 5-pound force straight up. I see that it's pointing straight up, and apparently that length represents 5 pounds. So if I wanted to apply a 10-pound force, I would simply draw a vector that was twice as long, right? There would be my 10-pound force applied in that same direction, right? Straight up, but a longer vector. So this gives me the idea that large forces are represented with long vectors, and weak forces would be represented with shorter vectors. And the same thing for large velocities and small velocities, and large accelerations and small accelerations. The length of the vector is its magnitude. So some notation about vectors. If I have a vector here that points from point A to point B, the point A is called its initial point, and the point B is its terminal point. And when we want to talk about vectors in writing, we can refer to this vector that starts at A and ends at B as the vector AB. And I would write that like that. Sometimes you'll see people draw a very nice full arrow on top, but traditionally a vector hat only has the one side of the arrow because we can draw that in one pencil stroke. All right, so this is how we write down a vector. The vector that points from A to B is the vector AB. When you see these printed in your book in typeset, vectors will be bolded. So in typeset, vectors will be in bold. So when you're author or on a lab or a test and I want to talk about the vector AB, we'll just make it emboldened. And right now we see how silly it is to try that in handwriting, but getting the point across, when I see vector AB in bold or with an arrow hat in either format, I know I'm talking about a vector AB. And it's important we denote things like that, right? I want to tell my reader I'm talking about a vector when I'm talking about a vector. So always use an arrow when you're writing out a vector in handwriting, because it will remind us that we're dealing with a quantity that has both direction and magnitude. Okay, one more little bit of notation and then one fact about vectors. The magnitude, or length, of a vector is denoted by this symbol. And this is actually what we call a magnitude symbol in a mathematics class, and it looks like a nested absolute value, right? A double barred absolute value. And this is a symbol I like for magnitude. So when I write vector AB in the magnitude symbol, I'm just asking for its magnitude, right? The how much part. So if I went back to my box being picked up, the magnitude of the first vector I drew was 5 pounds, and then the magnitude of the second vector was 10 pounds. Now, your textbook doesn't actually use this symbol. Your author uses the simpler absolute value symbol, and that's not inappropriate, right? Because absolute value is really a magnitude, right? Because if you were dealing with a velocity on a number line, negative means go that way, and positive means that way. If you take the absolute value, you're dealing with a magnitude. I prefer the magnitude symbol, but you will see a lot of textbook and places just use this as its magnitude symbol, and that's fine. So you'll probably see me use this one a lot. You'll see this one in the textbook, and we'll know they're the same thing, just talking about the magnitude of a vector. All right, and one last fact about vectors. Equal vectors have the same length and the same direction. So one way I like to think about this is if I take two identical objects, right, two marker caps sitting here, and I apply the same force to them, So when I say the same force, I mean the same amount of force and in exactly the same direction. The same thing should happen to these two identical objects. And so what I'm going to do is imagine just pushing the marker caps that way with the same amount of force in exactly the same horizontal direction. And both marker caps tip over. And I think I actually hit the purple one a little harder, but we can imagine that if I did exactly the same thing in exactly the same way, right? Same amount of force in the same direction, they would both topple over in exactly the same way. And there, they both topple over in exactly the same way. I would claim I used equal forces, even though I applied them at different places. And so that's why the requirement of equal vectors is just that they have the same length and the same direction. So, let's imagine two vectors in the plane. The first vector I'm going to think about is the vector AB, where point A is the origin, and point B is the point 2, 1. So here's A, and then the vector AB points from this point to this point. I want to draw a vector that's equal to AB, that has initial point C, and I'm just going to choose that to be the point 1, 3, and a terminal point that we're going to think up together. So my goal is to have a vector that's equal to AB, but starts at 1, 3. So there's my point C. And I actually think this is a good place for you to pause the video and just see if you can think your way through this problem. Where will the vector CD end? Where will its terminal point be so that it's pointing in exactly the same direction, it has exactly the same length as the vector AB? Okay, so the way I want to think through this is that if I start at A, to get to AB, I went over 2 and up 1. So I think if I just do that, over 2 and up 1, I should have a vector that's exactly the same length, pointing in exactly the same direction. So I went over 2 and up 1, so that should be the point 3, 4. Well, if I think about it, I went over 2 and up 1 in both cases, so the length is the hypotenuse of the same right triangle in either case. So the lengths are going to be the same, and we could calculate that, right? Just use the distance formula or the Pythagorean theorem. But when I think of direction, if I think about this as a rise and a run, these line segments have the same rise and the same run. They have the same slope, which means they're parallel. They're literally going up from left to right in exactly the same way. These are equal vectors.